A cardiologist can measure heart function in a number of different ways. One is an ECG, and that's a very easy thing that we can do. It's not invasive. It takes just a few moments to set up the machine, and you can get the electrical information you need. Uh, Unfortunately, that doesn't tell you volumes uh, that the heart is pumping. So, in order to determine volumes, we use what's called echocardiology. So, it uses sound waves to determine volume flowing through a heart. And those volumes can then be used to help determine heart function. So, some of the volumes we've already heard of are stroke volume, end diastolic volume, and end systolic volume. And we can put those in a simple formula, which is stroke volume equals end diastolic volume minus end systolic volume. So what that means is if you take the amount of blood that's in a ventricle when it's full and subtract out what is left in there after it contracts, you would get how much is ejected. So we can take and measure the volume in a ventricle and then calculate how much was pumped out. So you started with 130 and you're left with 60, you obviously must have ejected 70 milliliters. So that's one thing that this information can tell you. We also use these same numbers a little bit differently and come up with what's called the ejection fraction, which is how much by percentage was pumped out. So you use the same numbers. So it's stroke volume divided by end diastolic volume, and that gets you to a percentage. You have to multiply by 100 to get the percentage of that end diastolic volume. So how much by percentage was pumped out? And this is a very good indicator of ventricular function. So if you work with a cardiologist or you hear a cardiologist discuss a patient, there's a good chance that they're going to throw out that ejection fraction number. And rule of thumb is that a normal ejection fraction during rest should be somewhere around 50% or slightly higher than that. If there's an ejection fraction that's significantly lower, that could indicate some major heart problems. There's another number that we're going to use a lot, so we have to know what this one is. It's called cardiac output. And it's very simple. You're taking how much blood is pumped in a beat. So that requires you to know the stroke volume, which is the volume per beat. And then you multiply that by heart rate to get you how much volume per minute. So now we're looking at a time period. So how much volume total was pumped throughout an entire minute? So you take stroke volume times heart rate. And we can do that with our previous numbers. We can take 70 milliliters, which was our stroke volume. We can multiply that by 75, and you would get 5,250 milliliters per minute. But a cardiac output is usually represented by liters. So you just move that decimal place over 3 places, and you can go from milliliter to liter. And what's very interesting is on average, your cardiac output is about the same as how much blood you have. So a normal adult male has somewhere between 5 and 6 liters of blood. A female has somewhere between 4 and 5 liters of blood. And at rest, that entire volume circulates throughout the entire cardiovascular system in 1 minute. And that's at rest. If we were to exercise, we could get that cardiac output up 4 to 5 times that. So during maximal intense exercise, your heart is circulating over 20 liters of blood per minute, which is very significant. The difference between resting and then maximal cardiac output is often referred to as cardiac reserve. That basically means how much more could that heart circulate for you. That's what you have on reserve. So cardiac output is going to be an important one for us. We're going to look at things, conditions, nervous system, hormones, age status, things that affect cardiac output. And to affect cardiac output, you either affect stroke volume or heart rate. Quite often you're doing both. For example, when you're exercising, your stroke volume will increase. So the volume per beat goes up, say from 70 to 80, and your heart rate goes up. Maybe it goes from 75 to 125. So now you can dramatically boost that cardiac output by increasing both of these parameters. Let's look at your nervous system. This graph shouldn't be anything that new. You should have learned a little bit about the autonomic nervous system in A&P1 and how it affects your heart. This takes it just to the next level and looks at all the information that your brain gets to determine what it needs to do to the heart. So this is a very typical receptor monitoring information, monitoring stimuli, telling the control center, in this case it's known as the cardiovascular control center, and then that control center assessing all this information and then determining what to do to the heart. So let's go over this. Input. There's a number of different inputs to your brain. One is from the brain itself. So the cerebral cortex can have some input. Your limbic system, which if you recall is your emotional brain. So emotions can ultimately affect your heart. And then the hypothalamus. Hypothalamus, you can think about temperature. So body temperature also will affect your heart. Then you've got peripheral information. Proprioceptors monitor your body movements. So when your body starts to move, we need to tell the brain so it can tell the heart that it needs to pump more blood. Blood chemistry. That has to do with oxygen, carbon dioxide, and pH. So for example, if your carbon dioxide is a little too high and your oxygen's a little too low, we tell the brain, and then the brain can tell your heart, we need to circulate more blood to get more blood to the lungs so we can get rid of that carbon dioxide and pick up more oxygen. Then blood pressure. Blood pressure is monitored. So if blood pressure goes too high, we can respond by maybe lowering cardiac output to bring that pressure down. One thing to note, location. Proprioceptors are in your joints and muscles because that's where your body is moving. Chemoreceptors and baroreceptors are located in your carotid arteries and your aorta. And that information all goes to your medulla oblongata. So if you recall, that's this part of your brain. This whole thing is your brainstem, but just this area here is your medulla oblongata. It gets this information and then either sends out sympathetic activity or parasympathetic activity. Notice the sympathetic activity is done using cardiac accelerator nerves. And where those nerves come from is actually your spinal cord. So this isn't quite correct in that a nerve comes out of the brainstem right there and goes to the heart to speed it up. The nerves actually go down the spinal cord and then out. But those sympathetic neurons are going to increase heart rate and increase stroke volume. So now you got a boost in rate and a boost in volume. Therefore, you got a boost in cardiac output. Parasympathetic neurons are found in the vagus nerve. Your vagus nerve has most of your parasympathetic responses. About 80 or 90% is all vagus. That vagus nerve does come out of the brain because it's a cranial nerve, cranial nerve 10. So the parasympathetic neurons come right out of the brain in the vagus, go to the heart, and their job is to slow the heart rate. They don't decrease stroke volume, they just decrease heart rate. So that's your sympathetic nervous system getting information, processing the information, and then determining what to do to the heart. Final slide is a big one. It's got a lot of information. I think if you work slowly through this figure, it makes a lot of sense. But there's a few key points that you need to understand first. So what this figure does is talks about what are all the things, what are all the factors that ultimately affect your cardiac output. And this one talks about increasing cardiac output. A lot of these things you can think of the opposite, and it would decrease cardiac output. For example, if you decrease stroke volume or decrease heart rate, you would decrease cardiac output. Then this figure basically takes the top half and looks at all the things that increase the volume per beat, stroke volume. And then the bottom of the graph talks about all the things that increase your heart rate. So you got stroke volume on top, heart rate on the bottom. Let's look at the three categories that affect stroke volume. First one is known as preload. Preload, we're going to keep it pretty simple in that if the heart stretches, it produces a more forceful contraction. So if that heart fills with more blood, increasing its end diastolic volume, it acts like a rubber band in that it'll squeeze harder. And squeezing harder increases stroke volume. So that's preload. Contractility is very similar, but it doesn't have to involve stretching. So this is where the heart will contract harder, but not because it's stretched. So that's the big difference between preload and contractility. And there's a number of agents or a number of things that affect contractility. If you affect contractility, we call you an inotropic agent. If you increase the force of muscle contraction, you're positive. If you decrease the force of muscle contraction, you're negative. Notice all the things listed here that increase contractility. Therefore, they are positive inotropic agents. Sympathetic stimulation, we already talked about that. Catecholamines, which are epinephrine and norepinephrine. So those would be hormones in your bloodstream. Glucagon, which is also a hormone, can affect the force of muscle contraction. Thyroid hormones will increase the force of heart contraction. And then finally, calcium. The more calcium that your heart gets, the more forcefully it can contract. So those are things that increase the muscle of the heart. The third one is called afterload. This one, to keep it simple, you just think about the pressure your heart is working against, and that's inversely related. If the afterload is high, it's going to be harder to get blood out of the heart. So you think of the pressure in your aorta. If you increase that pressure in the aorta, it's going to be harder to get blood into the aorta, and your heart has to work harder. That's the problem with hypertension. When someone has high blood pressure, their heart has to work much harder to get blood out of it. So in this graph, it talks about the opposite of that. To increase how much volume is ejected, you want a low afterload. It makes it easier for your heart to work when your blood pressure is lower. But more often, we think about that in the opposite context. If someone has hypertension, high blood pressure, that's going to increase the afterload that the heart is working against, and therefore that can lower the stroke volume. So in order to compensate, your heart has to work much, much harder to overcome that high pressure in order to pump blood. So those are all on the volume side of things. On the bottom, the heart rate is a little easier. There's certain things that increase your heart rate, like your sympathetic nervous system, which we already talked about. Some chemicals, catecholamines, epinephrine and norepinephrine increase your heart rate. Thyroid hormones increase your heart rate. Calcium increases your heart rate. And then other things like infants and senior citizens typically on average have higher heart rates. Females do. Low physical fitness individuals, so like endurance athletes, will tend to have a well, they have high physical fitness, so they'll have a lower heart rate. Low physical fitness will have a higher heart rate. I forgot what I said, sorry. If you have a low physical fitness, someone who's obese, someone who's not very healthy, they will have an increased heart rate. If you have someone who's very physically fit, they tend to have a lower heart rate. And then finally, body temperature. Higher body temperature often results in a higher heart rate. Anything that affects heart rate we call a chronotropic agent. Chrono means time. So things that are positive chronotropic increase heart rate. Things that are negative chronotropic decrease heart rate. So again, heart rate is based on time, how many beats per minute, and therefore those would be chronotropic agents. They either speed it up, positive chronotropic, or slow it down, negative. You'll notice there's some things that are on both sides. If you look at sympathetic stimulation, it's going to increase volume and rate. So your sympathetic nervous system is both positive inotropic and positive chronotropic. A lot to chew on, but we're going to work on this stuff, and any questions you might have, please feel comfortable enough to email me or come see me.